Hello, everybody. Welcome back. All right, so I just had an issue with my desktop computer, so I'm switching to the laptop, and I guess we are fine now. Okay. All right, so today we will wrap up the what's left in the deep neural network chapter. We will cover the last part of uh, critical technique or technical methods or techniques that improve the training process, or how to say, to tuning a better neural network in a more efficient way. So we'll basically talk about two techniques. The first one is about how to initialize the weights. Okay, and I think comparably speaking, that is a relatively smaller issue. And the other one, the batch norm or batch normalization technique is, I would say, a technique at a higher level, with broader applications. Okay, so a bit recap or review of the previous lecture. We have actually introduced quite a lot of terms like dropouts and the L2 regularization in deep neural network too. So they basically deal with the overfitting issue because there are so many parameters in the deep neural network, and we want the network to capture the general patterns instead of the uh, idiosyncrasies, instead of memorizing the idiosyncrasies or stick with certain specific data points. That's something we want to avoid. So we introduce dropouts and L2 regularization uh, as a uh, uh, regularization term or technique. Okay, so also, we mentioned that in CV task, we can basically enlarge the training data size as a different way for avoiding overfitting, which can also count as a regularization method. Okay, so now we gonna introduce another issue that is very common in training a deep neural network. Okay, so it's called vanishing or exploding gradients. Okay, so the gradients is the quantities that we compute to update the parameters. So in neural network, it is usually computed from a backward propagation style. Okay, with and also the nature of the gradients is just the derivatives uh, of the cost function with respect to the parameters. Okay, so the issue is that in deep network, the gradients can get extremely big or small. Okay, so we can think about this issue. Uh, because this is the quantity we need to update the parameter, we use to update, right? It's a kind of the decides the how big a step that we want to take each time we go towards the minimum points of the cost function. And of course, this step is partially controlled by the learning rates. But if the gradient itself is too big, then the outcome, the results would also not be ideal. Or if it's too small, then the gradients, then the learning would be too slow, right? If you take too small a step each time, then it will take you forever to reach the goal. So uh, anyway, we want to kind of avoid this issue. So there are basically two methods that I'm going to cover here. First of all, uh, uh, which I didn't show here, the first one is a gradients clip, and it's basically to set a hard limits on the magnitude of the gradients. And the second strategy is to uh, initialize the weights in some particular uh, uh, under some particular conditions, so that the weights can help you avoid the gradients to vanish or explode. Okay, so let's look at how the exploding or vanishing gradients happened in the network. Okay, so let's assume that the biases are all zero, just for simplicity. So if we want to compute the activations from the last layer, right? The last layer is a capital L, and because there's no bias terms, and the result of AL is simply the multiplication between WL with the previous layer, and the AL minus one is also computed in the similar style. So anyway, we can chain the products in a way that we can basically express the final activation with a chain of products of that consists of all the weights in the previous layers from layer 1 to layer L. Okay, so in nature, essentially this activation is the result of applying a very long chain of products between weight matrix. So the issue with uh, this very long chain of products is that the value would explode if the weight has some very large numbers, right? So if they're like in this example, if there's a 2 in the weight matrix, then given L layers, then eventually the activations would be raised to the level of 2 to the power of L, which could be a very large number, okay? And what if the weight matrix contains small float numbers, small numbers that are under 1, between 0 and 1, then a very long chain multiplications will further squash that number, right? Or further reduce the magnitudes. It becomes a number that's almost 0, okay? So in either case, uh, the resulting activations would lead to uh, a very terrible um, gradients, okay? Because by the rule of backprop, we know that uh, the the gradients for dA1 is proportionate to those of dA2, and dA2 is also proportionate to the values of dA3, but we can have this, we will have these chains grow longer and longer until we trace back to the gradients of the last layer, okay? So the same thing would happen to the gradients. Um, I'm setting the weight matrices to identities because it's easier for demo, because when you multiply some identity, like some matrices with only the diagonal elements are non-zero, then you will result in another identity matrices, okay, which is just for simplicity. Because if there's non-zeros elements here, then the results would be like harder to describe, like harder to present here orally. Okay? Of course, this is not a hard requirement that all matrices need to be zeros in the non-diagonal area. No, that is not the case. So it's just an arbitrary choice of values. It could be any number. Okay, so um, yeah, the same thing would happen to the gradients, and we definitely want the gradients to be within a reasonable range, not to explode to some extremely big or vanishing to zero. So um, we can partially avoid this by setting the weights, the initial values of the weight parameters properly. Okay? So for example, if we zoom into one layer and with one output units here, then the output layer in if you focus on the second layer, which only have one unit here, the z's is a bunch of linear combinations between the activations from the previous layer, right? So um, we want the weights w's to be small and also has a variance that's close to this quantity, okay, to 1 over nl minus 1, which is the number of units in the previous layer. So that said, we are kind of approximating ZL by the average values of the previous activations, okay? So that's uh, the Z's, the variance of the Z's would be uh, almost close to 1. Okay, so the variance of Z's are not ridiculously large, okay? And the common practice is that um, we can randomly initialize the parameters at layer L uh, to a random matrix, but scaled down to the square roots of 1 over n and L minus 1. Okay. So this conclusion, um, if we want to explain why there is a square root of it, we need to read the papers that's from the guy who proposed this method. But it turns out that if we use this way of initialization, we will get the basically the best results of reducing the chance of exploding or vanishing gradients. But the thought is that we want to basically initialize the weight to smaller values, okay, that are that will help us um, um, average the activations from the previous layers. Right. So this way of let me clear the outputs, clear the drawings. This way of initialization is called uh, Xavier initialization. Okay. And it also from the original paper, it also points out that the way we want to apply, we want to adopt, also partially depends on the activation functions. So if there's a relu activations from the previous layer, then we will basically change the constants a little bit. Okay, so um, as I said, the y's are in the paper, and in practice, we will just call these functions to initialize the weights. Okay. So, and if we, for example, in the homework, if we want to initialize the weights, we should use the numpy.random.rand and to obtain some random numbers and then scale down them a bit. But we'll see that in the later demo, using PyTorch, we just use some predefined functions to set the parameters with one call. Okay, give me a second. My daughter is knocking my door. All right, sorry. Her class also begins at this moment. Okay, I think we are good now. All right, yeah, that's the Xavier initialization or Xavier way of initialization. So in PyTorch, it's just one call of these statements. Like if we first initialize a empty tensor in a dimension of 3 by 5, then we can call this auxiliary normal function, which means we draw the numbers from a normal distribution upon that tensor, and it will give us the better initialized tensor. Okay, so except for the weight initialization, we also often use the gradients clipping method to set a hard limit on the magnitudes of the gradients in a manual way. So PyTorch, I think it provides several methods like clip grad norm or clip grad value or something. So, but we can also write a custom function, like we can set some threshold, right? And given the model, we will set the values of all the parameters between the scope set by this threshold, which is between negative threshold and threshold. Okay, so we basically treat the parameters, the gradients of the parameters as some data, and we can manually limit the size, the magnitudes of those data. Okay, and I think people can adopt both ways, and it's sometimes it's quite the clip gradient. So this manual way should be enough to reduce the risk of exploding or vanishing gradients. So at least this is a more common way that I use. All right. Okay. So lastly, if you are unsure whether your gradients is problematic, then you can check the magnitudes of gradients and compare it with some approximated or estimation of the gradients. Okay, so how do we do that? How do we check whether our computation for DW, for example, DW or DB are correct? Okay, so we can use a different way to approximate the partial derivatives of the cost function with respect to the parameter W and B, and compare with the DW and DB, which are usually computed automatically or manually by backprop. And hopefully we want to see no big difference between these two values or these two quantities. Okay, so we can basically approximate the partial derivatives by changing the values of W by like a little step towards the positive side and a little step towards the negative side, and obtain the difference of the cost function and divide it by 2, the size of the total changes. And we do the same thing to estimate the partial derivative for B. And then we want to, we want to compare these two quantities. Like we want to compare whether the partial derivatives that we compute manually is almost the same as the gradients. Okay? So this is something we can try to use if there's a likelihood, if it looks likely that your gradients is a problem, then you can use this way to check. And you want to know which step or which layer or which component in your model that has a wrongly computed gradients. Alrighty. And this is just a different way or some more details for the gradients checking that I described. So the difference could be because you want to check whether the gradients are different from the uh, partial derivatives are almost the same. So we can use some extremely small epsilon to measure the difference. If the difference is below this quantity, then we can basically uh, claim that the gradients we computed is no problem. Okay, so that's gradient checking. Okay, so let's do one more recap for the all the things so far, all the bullets we have covered. So um, the I think one place that we may sometimes get confused with is the purposes or the goals for each technique. So, for example, for the dropout technique, the purpose is to avoid overfitting, and it belongs to the. If we want to summarize, if we want to summarize its purpose, we can say that this is a way to regularize or a way of regularization. And for the momentum RMS prop atom learning rate decay, they basically deal with the training, how to make the faster, making the training process faster, how to make the cost function converge to the minimum points uh, in a faster way. Okay, and for the um, weight initialization or gradients clipping, they also deal with the training process, but they are not for finding the correct gradients or finding the proper directions of gradients, but they are kind of reducing the risks of gradient. They deal with the magnitudes of the gradients. So they want to control the gradients within certain, within a reasonable range. Okay, so all these techniques so far, they um, help us to build a successful deep neural network model with from different perspectives. So um, lastly, we're gonna talk about the final technique, which is called batch normalization. So um, the original goal of it is to accelerate the training of uh, deep neural networks. So it's kind of overlap. They should belong to the first category. They want to, the batch norm will make the training faster, will make the cost function converge faster. Okay, but we'll see that it also uh, brings some effect of regularization. Okay? It also kind of makes the network less likely to overfit. Okay, so let's step into the details. So uh, first of all, we already have the idea that and we had this practice before in our assignments. We want to normalize all the features. We want to normalize the data, the input data, before we feed it into a model, feed it into a logistic or neural network, whatever model we want to use normalized features. Because if the feature is not normalized, then its space may be not in an ideal shape that is easy to optimize. For example, it could be in this very narrowly distributed. It may present some narrowly distributed contours, and the usual way of normalization is that we first move the to make the data centered around the 0 points, right? We basically shift data to 0 points by minusing the mean values from it. So here the mu's is the mean values for each feature. Okay? And also we can normalize the resulting centralized data by dividing with the standard deviations or the variance in each dimension. Okay, so this sigma is for the standard deviations. So after this step, because now it's totally normalized, then the data will be more beautifully shaped after the narrowly distribution is corrected to a more circle-like distribution. So the contours will be more normalized. So this is the shape that we want to have on the inputs because it will make the training more efficient. Okay, because if you look at the feature space and the cost function is the defined upon the W's and B upon your parameters. So if the feature space is in the more like circle, has a contours that are close to the circles, then the uh, cost function will traverse within these circle contours, which will make it easy to find the way that directly points to the uh, theoretical minimum points. Okay, but what if the the contours is not like regularly shaped? For example, on the left, it's a very long, narrow belt. Then the contours, they may point to um, directions that make more zigzags in the path from the starting point to the theoretical minimum. So that will require more, um, basically, more iterations in your uh, gradient descent step. Okay? So this is the normalization for the inputs. Right? We already know that this is quite necessary to train a model efficiently. And we basically want to normalize not just the inputs, but also the outputs from each hidden layer, right? If you normalize the axis, then why not also normalize those layers, the output from those layers? Because we can also treat the activations from the first hidden layer also as some inputs, right? Because if we use ReLU activation functions, these activations, they are not bounded, right? The ReLU on the right half, the ReLU function is not bounded. It's not bounded between 0 and 1, right? It could be any number. So it could be very large. It could be 0. Anyway, it's not normalized. So an unnormalized activations can still have the possibility to have a terrible distribution that is narrowly shaped. Okay, and we don't want that because those narrowly shaped distributions are hard to optimize, are hard to find the theoretical uh, local minima or theoretical minima. Okay, so the similar ideas will be applied. We want to normalize the activations in the hidden layers, okay, so that the parameters will be more efficiently trained. Okay, so in practice, we're not normalizing the activations, but the z's before we feed into the activation function, right? In each neuron, we have the left half, which is to compute the z, and the right half is to compute the a's, right? So we basically will normalize the z's in practice, and this is proposed first by Loaf and Shagady in 2015, which is called batch norm. So let's look at the implementation. Okay, so it uses a batch. So it's a operation that uh, occurs within a batch or within a mini batch. So this batch, the batch in the term here doesn't mean that we're using the whole data set, but we are actually focusing on a mini batch. Okay, so it's basically multiple training data points. Okay, so for layer L, um, for example, if we have n examples in the current batch or current mini batch, we can basically represent the z's in capital letter z as a matrix, right? And each column is the z's for one particular input example. Okay, so we have n columns from z1 to zn. Okay, and if we write those values with individual numbers, it'll look like this. And we have n rows because we assume the feature is has n the current layer has n neurons or n units. Okay, so we basically first need to compute the means. Okay, and within this batch, we can compute the means for per units across all the examples. We have m examples, so we'll compute the means for each units by summing up all the elements in that row and then divided by m. Okay, so it's like a per row mean values for the z's. Okay, so that is how we obtain mu, and mu is also a vector that has n components. And then we all need to compute the standard deviations, right? The variance we also need to compute, which is the difference, which is the sum of the square differences or mean square errors between the data points and between the z's and the mu's. Okay, so this is a quite standard mean square error computation. Okay, so after we have mu's and the sigmas computed, we'll use it to normalize the z's, original z's, right? So z will be subtracted from mu will be subtracted from each z and then normalized by the square roots of sigma square plus some small numbers epsilon to avoiding the dividing by zero error here. Okay, so that's how we get the z bars. Okay, and because this normalization will basically make the z bars to distribute it followed by this, described by this normal distribution. It has zero means and one as its standard deviation, one as variance. So that's the result we achieve by normalizing the z's. Okay, and we are not done yet. Okay, so the z bars is called the normalized output. Okay, but in practice, we're not just using the z bars, but let's use and define a new variable called z tilde with a little wave curve, like wave hats on top of z. It's called a z tilde. And this z tilde is defined using the z hat. And z hat is the normalized output because we want to give more flexibility to the model. We not just want to use the z tilde, but also we can make it give it more freedom to be scaled up or down to some different values. So we will let the z hat, z bar, to times some parameter gamma plus some new parameter beta. Okay, and in this case, the beta gamma, they are learnable parameters. That means they are part of the model. They are not the predefined constant hyperparameters. They are actually the parameters that can be updated by the gradients, updated by the gradient descent step. Okay, and they are also vectors. We have gamma, n gammas, and n betas in each layer of the model. Okay, so that the more flexibility are given so that the z tilde, they can have different mean and variance other than 0 or 1. Okay, so because if the output is between 0 and 1, then our model loses a lot of uh, expressiveness, right? It's kind of like we limit the input to some very narrow, we limit the activations within a very narrow scope or narrow range, okay? So this z tilde will be used instead of the original z's, right? Now we can see that originally we just used the z's, but now we use the z tilde. And this z tilde will be used to compute the activations, not the original z's, okay?
Here's a question about
Yes.
this slide. So it looks like, so every row, like where the cursor is the number of neurons in a layer, the number of columns, and the number of layers, or we drive that down.
Um, the each row, you mean what the number m?
Yeah, yeah, and
Yeah,
that's the matrix.
the m is the size of the current mini batch. We
Oh,
we have n examples in the current mini batch. Because uh, it's called batch normalization, we need to use the mean values within the current batch to normalize each column.
okay.
Each column represents one data point. So we need to use the average values, mu's, and the standard deviations, the sigmas, computed from all the data points.
Mhm.
Yeah.
I see. Okay, so it's kind of like, because then I think I wrote down something about the number of neurons in each layer too.
Mm.
It makes sense to me, like you have all these data points and you're averaging stuff from those. But
Yeah.
then the
We are
number,
not, yeah, you raise a good point. We are not averaging across the neurons.
just
We're computing the average value across all the data points, not across the neurons. So the number of neurons is n, is the small n,
mhm.
right? The lowercase z1 is the output from the first neuron, the first units. Z2 is from the second units. So these are not averaged.
I see. And that's because we're doing this for every layer. I
Mhm.
guess I'm thinking the
Yeah,
first
yeah,
one.
yeah, yeah. We're doing this for every layer. Yes.
I see. So in every layer, so if I have like the first layer, then all the data points that were put into that layer,
Mhm.
I look at, I average them all across each neuron. So neuron one comes with all this output, and I'm kind of averaging that. And then neuron two also took in all the different data points.
Yeah,
I'm averaging what neuron two got
yeah, yeah, yeah.
going down. Okay, I
Yes.
think that helps. Yeah, thank you.
Okay. So let's look at a more complete example. It's a two-layer neural network, and each layer has just two units, two neurons. So previously, we don't need that big big circle or big box because there's no complex computation inside each neuron, right? So the first layer we have parameters W1, B1, and we have Z1 and Z2 computed in the regular way. Okay, so then after the regular Z's are computed, we'll need to compute the Z bar, which contains the average values for Z, right? And after Z bar is computed, we'll need to compute Z tilde by um, using the some additional parameters, gamma and the beta. Okay, so this gamma and the beta, they are associated with the current layer. So I give them the one as superscripts. They are just like the W and B's. They belong to this layer. Okay, and they are also they are also vectors. So these particular gamma and beta for that layer are used to compute the z tilde. Okay, so that's what happens within the middle, in the middle of the neuron. So this is the so-called batch norm step. And the z tilde is computed, then the A1 is computed on top of the z tilde instead of the original z's. And these activations will be forward passed to the next layer. Okay, in which we have W2 and WB, and then we compute the Z2 in a regular way. And then, because there's a batch norm exists here, we need to compute the Z bar for layer 2. And also we have gamma 2 and the beta 2 associated with the layer 2. So we need to compute the Z tilde using these gamma 2 and beta 2. And then the activations from the second layer will be computed. Okay. So because one fact about the batch norm is that um, the Z tilde, when we compute the uh, Z bars, we are basically uh, um, subtracting the average values from the original z's. So the beta, so the bias terms, the b's for each layer, actually take no longer effects because the bias term is a add up term to each z. But since the average value, since the z's will be centralized around the zeros, it will the mean values are subtracted, so the bias terms will no longer take effect. So actually, the effective parameters, if we apply batch norm, is just the w, gamma, and beta, okay, for each layer. And the dimensions, they are so the gammas and betas, they are basically the same dimension as the bias, as the original bias terms. They are like the column vectors for each layer. Okay, so for mini batch gradient descent, if we apply batch norm, then we basically updating these set of parameters. We basically need to update we need to first compute the gradients for dw, d gamma, and d beta, and then we need to update those parameters. We just these are just uh, the same parameters, just like w and the bias terms. Okay, so that said, it means we can use momentum or RMS prop or atom just like the way we did for dw and db. Okay, so let's look at, okay, before we look at the effect of batch norm, um, the batch norm actually contains a pretty complex uh, mechanisms if we want to represent batch norm use a computation graph. Okay, so nowadays we don't need to implement the computation graph ourselves because it's all handled by the frameworks. But we need to, like I think it's in uh, um, uh, theoretically um, inspiring if we keep in mind that the batch norm actually comes with some additional forward pass and backward pass as defined by the computation graph. Okay, so the step from z to z tilde actually involves that many computations. First, the summation, right? Um, and subtracting something raised to the power of 2, right? Computing z bar and a bunch of multiplications. So all these are defined. If we define this computation, if we define the batch norm using this computation graph, the forward pass and the backward pass need to be taken care of really carefully. Okay, and fortunately, this is a very complex, although this is a very complex computation graph, we have already have them available in most of the modern frameworks. Okay. So let's see a little bit of why batch norm works. So um, uh, first of all, as I said, it's like just like the way we normalize the inputs. We basically avoid the narrow contours within the parameter space because we make sure that the activations are more or less normalized. Okay, and uh, in the theoretical arguments, I think it's in the original paper, the authors use the term covariant shifts. So it avoids the so-called internal covariant shift, which means the later layers are less dependent on earlier ones because all the layers they are all kind of normalized before the instead of using the raw inputs, we all uh, normalized all the layers to almost the same level. So they are less internal, less interdependencies within these internal layers. Okay, and more importantly, so I think the reason three is kind of related to reason one. It makes the uh, landscape of optimization much smaller. We will result in much more predictable gradients. Okay, so I guess this is results from a recent study that shows if we use uh, a batch norm as indicated by the blue curves, you will see a lot less jiggers in the not just the loss. So the first figure is the loss, and uh, the second is beta smoothness. I don't know what it is, but it may be some measurements of the landscape of loss. And the last one is gradients predictiveness, which basically measures how predictive the gradients. So as we see, the with batch norm applied, all those quantities they are more smooth, which means they behave in a much more predictable style. Okay, so this is something we want because we want the model to be tamed, to be like under control without too many uh, deviations from our expectation. Okay, so uh, okay, I see a question. For all of these models and optimization techniques we're learning, are of these considered standard practice for? Yeah, basically what we are talking about, we have covered in the slides, are all very common in the standard practices. Or should we interpret each technique as a way to help our training based on the intended effects of the model? Um, that's a good question. So do we need to uh, like explain or carefully separate the effect of different methods or different techniques, and to tell how they gonna affect our model individually or in a combined way? I think that is very hard. That is a very hard task. Uh, Basically speaking, we can use some like vague statements, like because we used dropouts and L2 regularization, so our model, they are more stable. They are all, so the model is, the resulting model is more robust against new data. It's less likely to overfit, or and that is something we can say, but nowadays I don't see a lot of people explaining that why they are using these techniques, why they are using like atom optimizer or momentum. So I typically the I just see in most papers I just see one or two sentences explaining that in order to boost the training, we use such optimization techniques and so on, right? And I think in top conferences like Neuro IPS, there should be a um, track or a circle of researchers that are interested to explaining the optimization techniques, like how different ways will result in different behaviors of the model. That is a very specific research area, I think. Okay, so one last point about batch norm I like to cover is about how to apply batch norm at testing time. Okay, so in training time, uh, when one mini batch comes in, we need to compute the average values. We need to compute the z bars using all the data points in the current mini batch. But in testing time, because we sometimes we don't have that many data points during testing in testing data, so we can the solution is we can keep the record or we store the running average of the mu's and the sigmas uh, that are used in the training stage. Okay, we just keep those numbers, these two numbers, the mu's and the sigmas that are the running average for all the training mini batches. And then we can uh, use those average values or exponentially weighted averages, which is a more fancier way, but I think sometimes a simple average is enough. And then using the average values and given a test example, we can compute the forward propagation by like compute the z bar using the running average. So we're talking about the testing case. So the z's are from the testing data. So the mu's is from the training data. It's a running average from all the training data points. And the sigmas is also from the training data points. So we can use the training data points to normalize the testing data points. And we just uh, use the um, resulting z bar like the way we did for the training process. Okay, so all these parameters they are now fixed because the training is ended. We just directly use gamma and beta as parameters. Okay, so that's for testing time. And maybe one more curve to show the effect of batch norm. So it can dramatically accelerate training of DNN. So basically in the original paper, the testing accuracy can very quickly saturate, which is the optimal points if we use batch norm. And also, it also serves kind of a regularization technique. And some people would choose not to use dropouts if the batch norm is already used. And so the thought is that basically the one training example is used in conjunction with other examples in the same mini batch. So the model parameters are determined by less likely to be determined by certain given examples because all examples are averaged. Okay, so the parameters are capturing um, more general patterns instead of the uh, remembering the most outstanding examples. Okay, and in batch norm in PyTorch is also easy to implement. We don't need to actually implement anything. We just call the functions. But sometimes reading the documents is not that straightforward if we don't have previous experiences. So I'm gonna have some demo code um, presented here after I finish the rest part of the slides. Okay. Okay, let me see how many slides I have. Okay, actually it's 3 or 4 now. 3 or 4 more slides. Okay, so all right. So instead of batch norm, we would have some variants, which is called weight normalization or layer normalization, but they basically belong to can be applied to different realms or different model, different tasks. But basically speaking, batch norm is the most commonly used way to uh, um, normalize the internal representations of each layer. Okay. So let's look at this systematic hyperparameter searching. So this is a different topic because we have that many hyperparameters defined in a model. We can basically, for example, if we want to decide how many layers or what the mini batch size could be, then we can randomly sample some numbers in the hyperparameter space. Okay, and we can zoom into, if we spot it, for example, if we spotted the best point is here, okay, then we can zoom into that area and do a final search if needed. Okay, so that point corresponds to the mini batch here and the number of layers here. So this number could be probably 32, or the number of layers could be 5, and so on. Right, so this uh, pretty straightforward method to find the best um, hyperparameters. And also, uh, for searching the initial learning rates, we basically don't sample in a linear space, because in the linear space, the uh, learning rates at 0.5, like learning rate of 0.5 is ridiculously high. But in order to do a systematic search for learning rates, we can use a exponential space, like uh, use alpha by randomly select the exponential term with a random integer number here, so that we are kind of randomly search within this exponential space. Okay. And uh, this technique, I would say that unless you are building some model, very totally new model from scratch, then if it's existing model, then you basically don't need to search the learning rates too much. It's just you just need to follow the practices from previous studies, and that is almost sufficient. Okay, so we have this table summarized functions and parameters and hyperparameters related associated to each technique, and you can use this table to help you review the whole chapter, the whole slides for the deep neural networks. So let's proceed on to the code demonstration now. Let me stop sharing the slides. And find my notebook. Okay, it's right here. Jupyter Lab. Okay, so hopefully it's big enough, right? Let me enlarge it a bit. So the first example is for batch norm. So first let me run the first cell to import torch and torch.nn. And what batch norm? The most common batch norm function in PyTorch is this nn.batchnorm2d. Okay, so these two, when we define this batch norm components, we call it M. Okay, which stands for model. So we need to specify the input size. So this input size actually um, specify in the computer's vision task is specify the number of channels. Okay, so here we define the input data by defining this random tensor. Okay, and this tensor has the size 10 by 3 by 8 by 8. So this is a very common practice that you will gonna encounter with if you are doing a machine learning task on image data. Okay. change overrides. So the first dimension 10 is usually the batch size. It says there are 10 images in this current batch, okay? And each batch has each example in the batch has the dimension 3 by 8 by 8. And this 3 is the number of channels because a color image has RGB channels, the red, green, and blue channels. It has 3 channels. And within each channel, it is a 8 by 8 pixel numbers. So basically the image is 8 pixel by 8 pixel as the width and height. Okay, so that is the usual how we organize the data, image data in a torch in a PyTorch tensor. So I use a random tensor, but I scaled up the values by 2 and shift the center to 4, okay? Because the original rand n will return random numbers with 0 means and 1 as standard deviations. So I change the inputs by scaling up the values, and I applied the defined batch norm upon the inputs and get some outputs. And I will take the first slice of image. So it's the first image and the first channel of the inputs. And the out 0 is the first image and the first channel in the outputs. And let's compare the difference between them. And in that way, we will see the functions of batch norm on the input data. Okay, so after I run the cell and scroll down, so I first print the in, right? The input is like this, and the outputs. So obviously it's much smaller value, right? And if we look at the mean and the standard deviations of the inputs, right? The mean is around 4 because I have a add 4 here, right? To force it to scale up, and I times 2 to the original random numbers. So the standard deviations here is also around 2. And but the mean and standard deviations of the outputs, right? You see is already uh, centered around 0. The mean values is centered around 0, and the standard deviation is around 1. So that is basically the function of this batch norm component does to the data. Okay, and in practice, we can embed this batch norm component within a very large a big model, like between layers. Okay, and second, we can look at the dropout technique that we talked about in the previous lecture, in the previous. So dropout, it also applies to the layer, to each, to a tensor, and then it will eliminate some values in that tensor uh, to 0, okay? And will also scale up the uh, values of the left non-zero entries in the input, okay? So this time I define the dropout unit with a probability number. So this probability equals zero point 0.5 means that I'm dropping out 50%, half of the elements in the input tensor. And the input tensor is a 4 by 5 matrix, right? And I will I will apply the dropout to it, and let's compute. Let's see the result, what the result looks like. So this is the inputs and the outputs. They are the same shape. The shape remains 4 by 5, but there are some zeros in it. And these zeros are the dropped out units or dropped out. Uh, okay, this one, yeah, this one. These zeros represent the dropped out units, and but the values of the remainings, they are scaled up a bit, right? So if you look at the norms, it basically uh, increases almost twice. So I guess this is a special mechanism defined by PyTorch, and they believe that if we drop out some units, we need to scale up the units by almost by the probability defined here, by 1 over zero point 0.5, which is almost twice as much. So this is the strategy taken by the PyTorch. I'm not sure if it's the same way of scaling up in other frameworks. Okay. But anyway, dropout is also easy to use in PyTorch. And lastly, we can see the uh, Xavier normalization. No, it's not a normalization, but it's a way to initialize the parameters. And this is code that I put in the slide. So if we run it, it basically return a bunch of random numbers that are follows the Xavier normalization, the Xavier initialization method. So all of these methods are all pretty easy to use and to call, and it's also easy to embed them into big models. And I can put this code online if you would like, and that is basically all the content we have today for um, deep neural network models. And I think by schedule, I should release the deep learning, the assignment for this chapter as well. I'll check my calendar, and if so, I will upload the assignment to Canvas by today. All right. Um, if you don't have further questions, I will end the class now. And yeah, so next week we're gonna enter the convolutional neural network, which is a big leap uh, that brings significant performance change um, to computer vision tasks. All right. So thank you for coming.